I'm really excited to be here today to tell you a little bit about the highs and the lows of our journey applying this method, smart casual verification, to our system, the Confidential Consortium Framework. Now, whilst I hope everyone's heard of the Confidential Consortium Framework before, I will begin by introducing it and telling you a little bit about why we wanted to verify it and why we chose the approach that we did. The Confidential Consortium Framework, usually just called CCF, is a platform for developing confidential, integrity-protected, and highly available applications, even when you're running these applications between multiple untrusted parties and you're running them on untrusted cloud infrastructure. It began life as a little research project in MSR back in 2017, and today it's an established open source project. We released our 6.0 release just a few weeks ago. It's used in production, and it's still being used as a test bed for doing interesting research into trustworthy computing. If you want to know anything more about CCF, do by all means ask me, or you can have a look at our GitHub repository. So whilst this talk isn't a talk about just CCF, I need to get onto the verification part. I just want to give you one slide to tell you a little bit about how CCF works. So CCF combines 4 interesting things. Firstly, we use trusted execution environments. This is a hardware technology that means that memory is encrypted, and even if you're running on a host that's up in the cloud somewhere far away, you can ask that host to prove that it has this special hardware that is doing the memory encryption and give you a digest over the code that's running in the cloud. This is a process called remote attestation. The first hardware technology to provide this was Intel SGX, probably the most famous, but there's many options now available, including AMD's SEV-SMP, Intel TDX, and ARM CCA. Then we've got some classic distributed systems. We've got some state machine replication, some transactions operating over a key value store. And we've got some more hip distributed systems inspired by permission blockchains and their interest in recent years. So we have a ledger that's immutable. We offer things like universally verifiable receipts over transactions in that ledger. And finally, we allow multiple parties to run an instance of CCF, and the way that they agree on how to run the system is through what we call the programmable constitution, which defines the rules of how the system is going to operate and how the system state can change over time. As I said, not just to talk about CCF today, so if you want to learn anything more about the architecture of CCF, please take a look at our VLDB paper from a couple of years ago. And CCF is not just a bunch of nice ideas in theory. This is Satya Nadella. This is him announcing the Azure Confidential Ledger service. This service is built directly on CCF, and CCF, as well as the Azure Confidential Ledger service, is used for a variety of interesting applications. I hope to have convinced you that developers and users are depending on CCF for some of the most critical aspects of their systems. And I like to sleep at night. I'm partly responsible for the distributed protocols inside of CCF. So I want to know that these protocols are correct and they're not going to break horrendously in production in a way that would give me nightmares. But if you look at the academic literature on distributed systems, we see so many examples of subtle bugs in distributed systems. Also, we see many companies failing in practice and talking about this in the wild. And these are smart people. These are smart people who are smarter than I am. And even then, we still find quite fundamental safety bugs in these systems. And it's just a hard problem, right? Distributed systems, you've got all the fun of concurrency and reasoning about concurrency combined with asynchronous messaging and partial failures. There's just a lot going on. And in fact, in the case of CCF, it's even harder. CCF's architecture is interesting, and I mean that in the full sense of the word. We've got some unusual aspects of the design. For instance, early SGX only had 128 megabytes of memory. And so our design was very constrained at the beginning by this memory limitation. And although this memory limitation no longer exists, there are still aspects of our design that are influenced by this early constraint. And so the question that we wanted to answer with this paper is how can we as a team increase our confidence in the correctness of CCF's distributed protocols? So we put together these 5 requirements for what we wanted from verification. The first 2 relate to the design of the system. We want to just document what is the design of the system, what can users and developers expect from CCF. And we want to check some high-level safety properties. You know, we say this ledger thing is immutable. How can we show that a transaction can't change? And the second lot, the third, fourth, and fifth ones are requirements about the actual running code. We want to have some confidence in what we're running, but unfortunately, CCF is an established thing that people are using. We can't just throw away all this work. As I said, we've been working on this since 2017. So we went and examined the landscape of verification approaches for distributed systems. And on one hand, you've got what we call casual verification efforts. This is essentially the software testing. So this is widely used. It's pretty easy. It can be really useful, and everyone should be doing it. And it works well whether your project is brownfield or greenfield. On the other hand, you've got formal verification. You've got fully mechanically proven implementations. I love this stuff. This is the intellectually satisfying stuff, right? This gives you guarantees not only about the existence of bugs, but the absence of them. Unfortunately, this requires significant investment of time, resources, and expertise. It's often a one-shot effort, and it's rarely used in production. And where it is used, it's best suited to greenfield projects where you are building the system from the beginning with verification in mind, which was very much not the case with CCF. So how can we achieve the best of both worlds? Well, we opted to use TLA+, it stands for the Temporal Logic of Actions. It was invented by Leslie Lamport as a way of specifying distributed and concurrent systems. It allows us to document the behavior of our distributed systems, hence satisfying our first requirement. And it also supports model checking. So a nice way to check some of these high-level safety properties without having to spend too much time fighting theorem provers. But what about our implementation, our big mountain of C++? Well, we actually did write the specifications, we did model check them, and we had our implementation, and we found that they were not in alignment. We had different people who worked on the specification versus on the implementation, and so they represented 2 different understandings of the system. We'd find ourselves tracking down bugs that existed in the implementation but not in the specification, and bugs that existed in the specification and not in the implementation. And even if we could have got these 2 things in alignment, there was no guarantee that they were going to stay like that. CCF is very much an active project. You can go onto GitHub and see what's happening. And so we wanted to get some guarantees of the alignment between the implementation and the specification moving forward. So what we needed was an automated approach to check for this alignment. This is where we introduce what we call trace validation, where we get behaviors, which are sequences of states, out of the implementation and check that these behaviors are valid in the formal specification, thereby tying, pun intended, the specification and the implementation together. So a little bit about TLA+. So a TLA+ specification combines variables which describe the state of your system, the initial state of your system, a set of actions that describe how your system state can change over time, and some properties that you would like to check. The specification therefore describes all the possible behaviors of a system. So you might have some initial state, here's some next states, here's some successors, some more successors, etc., etc. So one of our formal specifications that we wrote was for our consensus algorithm. So we model the set of nodes we have in CCF and their local states. And interestingly, we also very explicitly model the set of all in-flight messages. This was really neat because changing the data structure that we're using to represent the messages is an easy way for us to change the different network guarantees. This particular specification then includes 17 of these actions, which each represent one of the nodes in CCF taking an atomic step. This is always either initiated by a node receiving a message or timing out. Here's an example of what one of those actions looks like. This is an action that's called check quorum. And I will kind of read out in English what this TLA plus says. So this is saying check quorum of node I is equal to when the role of node I is leader and role prime, which means next, the role in the next state, and the next role is the same except that node I is now follower, and all the other variables in our system are completely unchanged. Once we've got those actions and those variables, we can then start to check properties. So mentioned before that we don't want transactions to be able to change, so we want to be able to say that no two transactions could be committed at the same index. And we can express this with the following pair of properties. So the first one, log in var, this says for any pair of nodes, their committed logs, one is the prefix of the other, or they are equivalent. And the second statement here, append only prop, says it's always the case that for all nodes that its committed log is going to be append only. So it's going to be the committed log before is a prefix or equivalent to the committed log after. So that's what we did on the specification side. There's obviously far more to it that you can find in the paper. But when it came to trace collection, we were quite lucky because CCF already had a test driver for things like mocking up unrelated components and injecting network faults. So what we decided to do was to instrument with these little if-def statements here, the implementation so that we could get access to some of the internal state. I think ideally we would just capture the network traffic between the nodes, but it turned out that this led to too much ambiguity and meant that we weren't able to check the specifications. We wanted to be as minimally invasive to the actual implementation as possible. That's why we constrained ourselves to these tiny little logging statements that basically just produce a JSON file of here was the state of the system at time step 1, at time step 2, at time step 3. Now that we got these traces, how did we actually check the traces against the formal specification? Well, interestingly, we were able to repurpose TLA Plus's model checker to check the execution traces. So we created a new trace for each of our specifications, which we called the trace spec. And it extends the original specification and extends each action in the original specification to say that the name of the step in the trace has to be the same as the name of the step in the action, and the variables, where they are available, have to be the same. We added just a simple line number, and we increment it at each action. We then check for the property that the line number that we're on will never be equal to the length of the trace. If we find a violation of this property, then we've just found a matching trace. So we've actually flipped it the other way. Usually we're talking about things like, these logs are immutable and those properties that we're expecting to always be true. And here we've actually flipped it. And so now we're showing a property that we're expecting to fail, and failure of this statement means that we've succeeded and we've got a matching trace. So how effective was smart casual verification? Well, it's worth bearing in mind that CCF was already very much proven in production and had been very extensively tested. But despite this, we found 6 subtle bugs in CCF. All of these were found and fixed before they were able to cause any issues to customers in production. There's a table here, and in the paper we walk through in detail each of the bugs. So I mentioned that I would tell you a bit about the lows of this work as well as just the highs. By far the hardest technical challenge was the fact that we didn't build our implementation or our specification with the intent of doing this trace validation. So that meant that there wasn't a lovely one-to-one correspondence between actions in our trace and what was going on in our implementation. So for instance, we have things like in the specification, we have this idea that you can have a complete copy of what's going on in the ledger, this append-only data structure. But in practice, we don't want to log the full state of the ledger at every step because that's going to grow far too fast. And also in our specification, we have an event like network dropped a message. Obviously, in practice, when network drops a message, it's just a thing that just quietly happens, and you don't know that it's happened until you never see the receipt of the message. And so we had these different kind of granularities of atomicity and different sets of variables and different actions between the two. And so we have quite a bit of ambiguity that we need to carry through when we're doing this trace validation. Secondly, debugging trace validation can be tricky. So one of the really cool things about TLA Plus is that when you're checking some invariant and it says this is violated, it gives you a nice counterexample, and you can say, oh, look, I can see what went wrong. This thing, this thing, this thing, this thing happened. But because we flip that and we're looking for that counterexample because that's the matching trace, when it doesn't find a matching trace, it just terminates, which is quite difficult to debug. And finally, and this is much more of a fundamental kind of existential challenge with this approach, and that is trying to quantify how good the coverage is that we actually have achieved with trace validation, like how much trace validation is enough trace validation. At the moment, our constraints really are that we run a CI that does trace validation on every single commit to CCF, and basically engineers will only wait so long for the CI to go green or red, and so that's the amount of trace validation that we do. But is it enough? Have we done enough? Is there bits of the code that aren't being exercised? How can we measure it and improve it? So that's it for me. I really would encourage you to have a look at our paper, which dives into much more detail about our journey with smart casual verification, which is an approach that combines the rigors of formal specification and model checking with the pragmatism of automatically binding together the specification and implementation. And with that, I will take any questions.